Oh boy, now we get to talk about rigging arms. I'm going to try and cover a variety of things in this video, so bear with me. The first thing is how to do IK-FK switching. We want Mr. Hot Dog to be able to swing his arms around, which is a lot easier to do with an FK rig, but we also want him to be able to hold on to things, which is a lot easier to do with an IK rig. So the obvious solution is to allow the animator to switch the arm controls between FK behavior and IK behavior. There are a variety of ways that we can accomplish this. The first way depends on the fact that an IK bone chain is nothing more than an FK bone chain with an IK constraint on it. If we add an IK constraint to this bone chain, then we can control it with the IK target. But if we simply slide the influence of the IK constraint to 0, then we can use the arm like an FK rig. This is probably the simplest possible way to do an IK-FK switch, and for some rigs this may be enough. However, there are some problems with this. The biggest issue with doing things this way has to do with how inverse kinematics calculates the rotation of bones in an IK chain. Inverse kinematics figures out the rotation of bones based not just on where the IK target is, but also based on where the bone chain started. So, for example, right now if we switch IK on, the bones are put into this position. But if we change the FK position of the bones to bend the other way, then the IK solution bends the other way. And this problem only gets worse when we throw in pull targets. Basically, it makes things unpredictable for the animator, since the IK arm will behave differently depending on what they do with the FK arm. So if this is such a problem, why does Blender do things this way? Why not base it on the edit mode rest positions of the bones, for example? Well, the reason Blender does it this way is because it's actually a really good thing, and in other circumstances it allows us to do a lot of cool things that would otherwise be impossible, which I'll be getting into later in the video. It's only a problem in a few circumstances like this. And besides, we can work around it. So let's figure out how to do exactly that. The important thing here is that we don't want the IK bones to be directly rotated by the animator, right? So one way we can work around this is to make a duplicate bone chain that follows the IK target, and instead of turning the IK constraint on and off, we have copy rotation constraints on the FK bones that get turned on and off. If the IK chain is a hidden mechanism bone chain, then things will look identical to the animator, except they won't accidentally mess up the IK. So let's try that. Make a duplicate bone chain, offset it vertically a bit so we can see the difference between it and the original. We'll move it back later. Now delete the IK constraint from our FK chain, and let's constrain the FK chain to the rotation of the IK chain. Just add copy rotation constraints between the respective bones. Now if we move the IK target around, you can see the FK chain duplicating the IK chain's motion. Let's move the IK chain back down to match up with the original, and move them to a hidden armature layer. Now the FK chain is behaving exactly as if it were the IK chain. But if we turn off the copy rotation constraints, then it becomes an FK chain. But because the IK chain is not being affected by this at all, when we turn the copy rotation constraints back on, the chain goes back to the same position as before. It's consistent. And in a final rig, of course, both copy rotation constraints would be driven by a single custom property, so even though as riggers we have to manage these two separate constraints, the animator won't. The only thing we really need to do now is add bones for the hand. When the animator is using the arm with IK, it makes sense for the IK target to serve as the hand control, so let's orient it a bit more sensibly for that purpose. However, it makes very little sense for the IK target to be the hand control when the animator is using the arm with FK. Ideally, we'll want a separate control that is directly part of the FK chain. So let's duplicate the IK target, and make that duplicate part of the arm chain by parenting it to the FK arm chain with connected. And let's constrain its rotation to the IK target so it follows the IK hand when we're in IK mode. Try this out now. Yay, it works! The character, in this case, would be parented to the FK chain, which does its own thing in FK mode, but copies the IK chain and controls when in IK mode. So this is a pretty nice solution. In fact, I think this is a perfectly fine solution for most rigs, and for Mr. Hot Dog I would be fine stopping here. But in the interest of teaching you a more complete solution, we're going to go a little bit further. The main problem with this solution actually has nothing to do with animators. The problem is that this actually makes things more difficult for us riggers. Let's say we wanted to add squash and stretch to the FK arm rig. Well, with this rig, we would have to be really careful about doing it in a way that wouldn't interfere with constraining it to the IK arm rig. And that's annoying. It would be a lot nicer if we could, as much as possible, completely separate the FK and IK rig so that we can think about the features and solutions for each rig separately. Remember that it's nice to rig in parts, so that we can focus on one problem at a time. We don't want things to get unnecessarily mixed up. Fortunately, this is an easy fix. All we have to do is introduce a third bone chain. The idea is that we have the FK rig on one side, and the IK rig on the other, and then we have a third bone chain in the middle that switches between copying the FK rig and the IK rig. The character will then follow this third bone chain. This way we can think about the FK and IK rigs completely separately, and we can then deal with how to construct a bone chain that can copy both as a separate problem. This also has a side benefit for animators, which is that they never lose their FK controls. With our previous rig, when we switched to IK, the animator had no way of positioning the FK version of the arm. This isn't critically important, but it can be useful when the animator wants to switch between IK and FK mid-animation. So let's put this into practice now. Remove all the constraints from the FK chain. And let's also move the IK hand to another armature layer so we don't get too confused. Now let's duplicate the FK bone chain and move it up a bit. This will be our intermediate chain. Also, move it to its own layer, and enable that layer so we can see it. Now constrain this rotation to the FK chain. And now let's name the constraints. Wait, what? Yes, that's right. We can give names to our constraints. For simple cases, this isn't really important. Heck, I'm not even naming the bones right now, since this is just our rigging playground. But in the final rig, we'll want things named for clarity. In this case, it will be nice to see at a glance which constraints are for FK and which are for IK. So name all of these constraints FK. Now hide the FK layer, and unhide the IK layers. And constrain the intermediate chain to the IK bones. And name those constraints IK. Now unhide all of the layers, and let's play with this. Right now it's following the IK chain. That's because we added the constraints for the IK chain after the ones for the FK chain, so they're later in the stack, and therefore overwriting the constraints to the FK chain. But if we slide the IK constraints influence to 0, now it follows the FK chain. So in the final rig, all we'll need to do is drive the IK copy rotation influences with a custom property, and bam! Instant IK-FK switch. And of course, in the final rig, the intermediate chain will be in the same position as the IK and FK chains, not offset vertically. I just have it offset so it's not so confusing when we're building it. So are we done now with the arm rig? Well, no. We now know how to switch between the IK and FK rigs, but we still need to design each of them. Yeah, this is a long video. Sorry. So let's start with the FK rig. You might think there's really nothing more to an FK rig than just having a simple FK bone chain, and you would almost be right about that. But there's one teensy-weensy feature that can make things a lot nicer for animators, and that's the ability for the arm to not follow the body's rotation. Let's say we have a character jumping up and down, waving at someone. The body would be rotating back and forth as part of the jumping, but the arm would be doing its own independent rotations as part of the waving motion. The problem is that if the arm is simply the child of the body, then it's going to be following the body's rotation, which the animator will then need to counter-animate against. When I was animating on Big Buck Bunny, this was actually a huge problem with the rigs. And Unfortunately, I had no one to blame except for myself, since I did the rigging for it. And I cannot tell you how much counter animation I did on the character's arms. It was a lot. That's not to say that limbs aren't affected by body's rotation, but it's a loose, indirect relationship. If I swing my body around, my arms have a delayed flopping reaction, and having the arms follow the body's rotation directly would actually hinder, not help, an animator achieve that effect. In fact, having the arms follow the body directly is so unhelpful that I have often been tempted to just remove that behavior from my rigs entirely. However, there are a few circumstances where it can be helpful, like with, robots, I guess. Or a character doing the robot. So, we're going to make it something that the animator can turn on and off with a slider. The process for this is actually really simple. It's almost identical to the switchable parent, actually. If you think about it, all we really need to do is make a switchable parent, except we want the bone chain's location to stick to the parent even when the switch is off. So all we need to figure out is how to make the bone chain's location stick, because we have the switchable parent figured out already. So we have a body bone and an arm chain here. If we want the arm chain's location to stick with the body bone, we can do it with a simple copy location constraint. So constrain the base bone of the arm to the location of the body bone. Well, although this works in a sense, this obviously isn't quite what we want. We want the bone chain to stay in the shoulder socket, not the hips. But this is pretty easy to do. Just add another bone where we want the arm bone to stick, and make it the child of the body. Since this bone is the child of the body, it goes with the body. And now we just have to constrain the arm to this bone. And now if we move the body around, the arm sticks, but it doesn't follow the rotation. This is exactly what we wanted. Excellent. I like to call this a socket rig. This extra bone we added is kind of like a socket, and the arm stays in that socket. Now to make it switchable, we just have to layer on a switchable parent. There are actually multiple ways to do this, but I like to try and keep all of the constraints on a single bone when reasonably possible. So for the arm's real parent, I'm simply going to make a duplicate of the socket bone, and unparent it from the body. And make the arm the child, of course. Now remove the constraint from the arm. The arm is no longer connected. Now just add the copy location constraint to the parent instead. And as long as the parent and the arm are in exactly the same location, this behaves the same as what we had before. We also have the bones needed to do the parent switch. Just add a copy transform constraint between the socket bone and the parent bone. Now the arm behaves as a child of the body. But we can turn that off by just turning the copy transforms constraint off. I like to call this rig a socket switch. And that's pretty much it for the FK arm. We just need to choose our rotation modes and access locks. The upper arm rotates on all three axes, so it makes sense to leave that as a quaternion. Otherwise, you can run into major gimbal lock issues, especially in combination with a socket switch. However, we don't want the animator to accidentally pull it out of its socket, so let's lock the location axes. The forearm only rotates on one axis, so Euler rotation with only one free axis makes a lot of sense here. And we're just going to leave the hand alone. It's not horrible to set the hand to Euler as long as you choose the rotation order well. After all, it mostly just rotates on two axes. Mostly. But I like to leave it as a quaternion, since it will be more consistent with the IK hand. The IK hand will be quaternion since it's floating in space, and needs to rotate on all three axes to orient itself in various ways. So that's it for the FK arm. Hurrah! For the IK arm, we also don't have a whole lot to do. In fact, we're going to do nearly exactly what we did for the IK leg rig on Mr. Squeegee Feet. So I'm not going to cover that again, just go back and watch that video. But I do want to expose you to three things. The first is a clever little trick I figured out not too long ago. The second is an alternative way to control elbow and knee direction. And the third is showing the weird way that IK interacts with the constraint stack and how to work around it. So first, the trick. Remember way back in the squeegee feet tutorial, I told you to keep the knee bent in the default position? Well, now you know why. It's because the IK solver uses the initial position to determine how to make it reach the IK target. In particular, the knee will tend to bend in the direction that is already bent. But now that we know that the IK solver uses the current pose of the bones, not their edit mode positions, we can use a trick so we don't have to have the edit mode bones slightly bent. This can be really useful. Sometimes the models we want to rig have straight arms or straight legs, which means the edit mode positions of the bones need to be straight too. We have here a totally straight bone chain. If we turn this into an IK chain, it can't decide which way to bend and it kind of freaks out. But even though it's not bent in edit mode, we can just manually bend it in pose mode. And now it works just fine. Cool, right? However, we don't want to rely on this pose adjustment staying put. Even locking the rotation axes isn't enough to make me comfortable with this, because the user can still manually adjust the numbers. They're really only pseudo-locked. But remember earlier in the 3D ball chapter, when we wanted to lock the rotation mode of a control? We just added a driver to it with a simple number as the driver expression. We're going to do the same thing here. Right-click on any of the rotation channels and select Add Drivers, plural. If we go to the drivers interface now, we can see that Blender automatically filled in the driver expression with the current value of the channel. Blender will automatically do this for numerical fields like the transform channel, so we don't actually have to configure the drivers at all. That makes adding drivers a convenient way to lock almost anything in a rig. And that's the trick. Just bend the forearm bone in pose mode, and add drivers to the rotation channel. Your arms can then be as straight as you want in edit mode. I like to call this IK hinting, because we're giving the IK solver a hint about how we want it to position the arm. The next thing I want to show you is an alternative way to control the knee and elbow direction of an IK chain. I've already set up a basic IK arm, with the elbow locked to only rotate on a single axis. The way we did this on the leg rig was to add a pull target that the knee points at. But if we want to, we can instead take advantage of the fact that inverse kinematics solves from the posed position of a chain. If we give the chain a parent, then we can rotate the parent bone to determine the elbow direction. This works because under the hood, if we turn IK off, the arm chain is rotating along with the parent. So when the IK is active, it's calculating things based on that starting position. This method can work pretty much just as well as the pull target method, and the animator can more or less think of the elbow as pointing in the same direction as the parent bone. The only thing to be wary of is that the twist of the parent bone needs to not stray too absurdly far from the IK target, because then it starts doing weird things. Although it is still pretty forgiving, but it can sometimes be a bit more for the animator to have to think about, and it may not always be obvious to the animator why it behaves weirdly. But still, for some situations, I think this method of controlling elbow and knee direction can actually be better than pull targets. It just depends on the situation. For Mr. Hot Dog, we're still going to stick with pull targets, but I just wanted to show you this because it can be useful. So the last thing that I want to talk about is how inverse kinematics fits into the constraint stack. The tricky thing about inverse kinematics is that, unlike most other constraints, it affects multiple bones. And because of that, it always gets applied after all of the other constraints on those bones. To understand why, let's take a look at yet another silly little drawing. We have 3 bones here, each with their own constraint stack. The last bone has the IK constraint on it, but that constraint actually affects both of the other bones. So if the IK constraint is, say, in the middle of the last bone's constraint stack, when should it be applied to the other bones? I suppose it could just be applied as if it were in the same position on the other bones, but if we did that, then even if we put it last in our last bone's stack, it would still only be applied partway through the first bone's stack, which would be confusing. But it gets even more complex than that. You see, multiple IK constraints can actually work together on a branching chain in Blender. If there's an IK constraint on this bone that affects bones all the way back to here, and there's another IK constraint on this bone that also affects bones all the way back to here, then the two IK constraints need to cooperate on the shared section of bones. And that means they both need to be executed at the same time. But they're two separate constraints and could be in completely different places in their bones' respective constraint stacks. So in order to avoid all of this confusion, the IK constraint is considered unique, and instead of getting evaluated where it's placed in the stack, it always just gets evaluated last. That pretty much makes sense. Except, what if we want additional constraints to be applied after the IK constraint? Fortunately, there's a cool trick you can use to accomplish this. I have a simple IK chain here, and the main observation we need in order to get around this limitation is that the IK constraint is only executed last on the bones in the IK chain, not on any other bones. So if we make a duplicate of this chain, and we constrain the duplicate chain to the IK chain via copy transform constraints, then the second bone chain now does exactly what the IK chain does, except we can add constraints after the copy transforms. So the second chain is basically just a way to extend the first chain's constraint stack. Back to silly drawings again. Essentially what we're doing is applying all of the constraints we want to happen before the IK constraint, then we have the IK constraint, then we transfer everything to another bone chain, and then we apply all the constraints we want to happen after the IK constraint. Then you can attach the character mesh to that second bone chain, or it can be part of some larger mechanism, or whatever. Anyway, I haven't actually used this in a rig quite this directly yet, at least not that I can remember, but it's worth being aware of. You can get around the fact that IK constraints are always executed on a bone last. So there we go. That's everything that I wanted to talk about in this video. Whew,